and welcome to Chalmers from a Student 2022 design presentation. So, my name is Andreas, and this is the agenda we're following today. We're going to start off what is Formula Student, and then a little bit more about us, Chalmers from a Student, and then we'll eventually get into more of the technical, the car design, and we're going to finish off with some open questions for everyone, and we'll have some mingle just outside where you entered. So, what is Formula Student? It's the largest engineering competition for students, and it works in a 10-month cycle usually. And there are over 600 different teams worldwide that are competing in Formula Student. And what we do is we design, build, test, sell, and eventually race a Formula-style car. And we compete in both dynamic and static events. And this is to test the entire and complete engineering challenge. So it all started back in 2001 when CFS was founded. And back then we were using a combustion car engine. So it was two-wheel drive. And we had some good success with it in 2012 and 2014. And eventually we went with electric. We started off with a two-wheel drive car there as well. And we had some great results there as well. And eventually in 2019, we went with a four-wheel drive system. And then what's new this year for 2022 is that we're going driverless. So this year we're gonna go have a car that can drive both with a driver in it, but it's also gonna be able to drive driverless. And with this comes a number of new technical challenges, and that's what we're gonna dive deeper into later on. So who is building this car? It's us, Chalmers from a Student. We're a team of 43 project engineers that do this at full time. We have 19 trainees helping out, and we have about 8 managers making sure we're doing what we should. And we come from a lot of different areas of study, over 15 to be specific. And we are a very international team. We have over 10 different nationalities in the entire team. And I'm very happy to announce that we will go to 2 different competitions this summer. Formula Student Austria, where we're going to be driving a manual car. And we're going to be driving at the famous F1 Red Bull Ring track. And then we're also going to Formula Student East, which is in Hungary, where we're going to be running the car 100% driverless. And then, as I mentioned earlier, for the Complete Engineering Challenge, these are the events we're going to be competing in. So first, for the static event, I told you we have to sell the car. So we have to pitch a business plan idea for a few referees or judges, where we have to show that we can pitch a good idea and sell it. We also have the custom manufacturing event, and what this is that shows that the team are good at making up the budget and economy of the car. We have to show that every piece of the car is written down, and every process that goes into making the car is also written down. You can't build a car if you don't have the economy for it. So we have to show that we are able to do that. And then the next event is the engineering design event. So what we do here is we get different referees or judges from specific subgroups, or they have expertise within certain areas. And what they ask questions about the car and what choices we have made. And we have to show that our choices for the design has been data driven. We cannot just say that, oh, the other teams did it and they did good. We have to show that why is it good for just our car and just our team. Then we have the dynamic events, which includes driving. And here we have endurance, which is a 22-kilometer long run. We have to drive as fast as possible around several laps around the track. And we also have to do it as efficient as possible. We then have track drive, which is the new event for this year. And here we're going to be driving the car about 5 kilometers around several laps around the track, but this time with only driverless doing it. I'm sorry, endurance also is a manual competition, and track drive is a driverless event. And then we have autocross, and here you just have 1 lap around the track as fast as physically possible. Nothing with efficient, just as fast as we can. We then have acceleration, and this is just a 75-meter long straight. We go as fast as physically possible here, and this is run both by the driverless and the driver. We then have the skid pad, which is the last event. And here's a picture of it. It's a figure 8 where we test the lateral acceleration of the car, where we run both with a driver and driverless. And we try to set as fast as possible, the fastest possible time.
And to start off, we're going to start off big by showing the 22 car. Some technical highlights of the car include 97% of what you see here is designed by us and manufactured by us. In each wheel assembly here, you can see there sits one outboard motor giving us 4-wheel drive, and all of these are hand wound. And apart from milling of the molds, the entire monocoque is a long process that basically we make it ourselves, just like everything else. Here in the rear compartment, you can find the battery and the electric powertrain. And outside here, you can also see the aerodynamic package. Every part of this car is optimized to reduce weight and inertia, allowing us to accelerate and turn quicker and eventually reduce our lap times. To our acceleration speed, from 0 to 100, we can achieve that in 2.5 seconds. To dive deeper into the specific subsystems, we will begin with aerodynamics, where I will hand over to Linnaeus.
Thank you, Jacob. Yeah, let's talk aerodynamics. Why do you need aerodynamics? Well, aerodynamics gives you downforce, and downforce gives you increased grip, and increased grip gives you more cornering speed, and that reduces lap time, and you get more points on competition. So, this year's aerodynamics package was an uphill battle, because we had to add a lot of new components to compensate for the driverless system. So we added a additional computer, a LiDAR, and a camera, and a lot of other stuff. So we started off with a really low downforce level, but we're really proud to say that we increased from that level at the start of the design period, increased that with 22% to the end of the design period. And we did that by changing our parts, of course, but also taking into account the new parts and giving them casings for like the driverless computer or the LiDAR. And that gives us an aerodynamic package that makes it so the car can be driven upside down, theoretically, at 120 kilometers an hour. We will not perform this stunt, but that's just a fun fact. And lastly, the aero package will be manufactured with the carbon fiber, and this is because carbon fiber gives you a high stiffness and strength to weight ratio. So our aero package will be very light at approximately 12 kilograms. Yeah, and Daniel will take you through more on the parts.
Yes, talk more about the specific components of the package. First off, we have the front wing. This is the single largest contributor of downforce on the car at about 35%. We're very proud this year to have improved the braking performance of the aerodynamic package. That is the downforce produced by 25% compared to previous years. The front wing is mounted to the monocoque using the brackets here you can see. These are topology optimized to reduce the weight, but still keep all the strength. New for this year is that we have a drag reduction system on the front wing. This means that the flaps on the front wing can open up on the straights to reduce the drag and therefore increase the speed and efficiency. We also have a rear wing. This is optimized for the maximum downforce at around 25% of the total produced. This front wing also has topology optimized brackets and a very strong DRS system that reduces the total drag of the car by 40%. On the sides of the car, we have the side structures. These are mounted on the side of the cockpit, besides the driver. This is a component that has been producing more and more downforce each year, and it's now up to 25% of the total. New for this year is that we have an integrated cooling package, which means that the fans and radiators are mounted so that suction is increased underneath the car, producing more downforce, and also the fans are mounted in a way such that airflow is directed to the rear wing, increasing the downforce of the rear wing even more. We also have side covers that house the driverless computer on the side of the car. Lastly, we also have the rear diffuser. The rear diffuser increases the downforce of the car's underside, the whole chassis of the car, and increases around 15% of total downforce. This is designed to be easily removable, to easy access to the electronics in the rear of the car. New for this year is that it's larger than ever before, due to it being integrated with the monocoque that has a slant at the rear. Gabriel will now talk more about this monocoque.
Thank you. So yes, the chassis group. This is the group that is responsible for designing and manufacturing the monocoque that all other parts of the car is mounted to. This year, one of the big things has been introducing a slant to the rear compartment. This is to allow more efficiency from the rear diffuser that Daniel was just presenting. We've also had to accommodate a lot of changes for the driverless systems, the visibility of sensors, etc., that we haven't had to take into account previous years. One of the big goals has also been to increase the torsional stiffness of the monocoque, because having a stiffer chassis allows for more tuning of the suspension geometry. Another important part for the chassis group is to do a lot of material testing. Since we are putting a driver in this that are going to be racing at high speeds around tracks, we need to make sure that the car is safe in case of a collision. For this, we do a lot of material tests, both for layups and in the case of crashes. We also want to optimize this so that the chassis weighs as little as possible while still keeping the driver safe. Now to present more about the moving parts of the vehicle, Herman is going to take over.
Yeah, so I represent the wheel assembly group, and our mission is to get the power from the motor to the ground. To do this, we have this wheel assembly here. The biggest change this year was the fact that we moved from an 18-inch tire to a 16-inch tire. This was mostly done to reduce the rotating weight as well as inertia of the whole assembly. Together with other light or weight reduction things we did, we managed to reduce the mass of the system with 4.8 kilograms, as well as reduce the rotational mass with over 800 grams per wheel. This is of course very important to improve the handling of the car, as well as the responsiveness during acceleration. Other than that, we try to improve the make the system more reliable by reducing the amount of parts, and we also tried to get common parts so we could have interchangeable spares for the front and rear axle. As Andreas mentioned in the beginning, we have a four-wheel drive system on the car. So we are not only using motors to propel the car forward, we can also use the motors as generators during braking to recoup some of the power that would otherwise be lost into heat during braking. The maximum combined power of our tractive system is 80 kilowatts, and that is due to regulations. And our system produces a maximum torque of 1250 Newton meters. To dive a bit deeper into the system itself, we have our homemade carbon fiber rims. And one of the biggest reasons to use carbon fiber rims is of course to save weight. But we also are very free in the whole packaging design when we do them in-house, because we can change the offset and the bolt pattern of the rims very easily, and thereby making a more well packaged system. Then we have our gearboxes. So they are here, and they are single speed reduction gearboxes. It takes the approximately 20,000 RPMs maximum from the electric motor and transform it down to a more usable rev range and increasing the torque as well. We have the floating gearbox assembly, or the floating disc brake assembly. which of course is used to stop the vehicle. We have 4 piston brake calipers in front and 2 pistons in the rear. The reason for using floating discs is of course that they won't warp when they get hot. Then we have our uprights. They are used to connect the suspension linkages to the assembly. They are made or designed by utilizing topology optimization to try to get as stiff and lightweight component as possible. They are done 3D printed using metal 3D printers, so they are printed in aluminium. And then we have our electric motors. They produce 32 kilowatts each. So the excess power that we have, we use to do torque vectoring, which means that we can have different amount of torque applied on each wheel, and thereby trying to get it through corners faster. Lastly, we will look a bit into the gearbox itself. It's a planetary gearbox. It's a 1.5 stage gearbox, so it takes the power from the motor in here. Then we have the planetary gear set, and then the ring gear. The ring gear is mounted to the gearbox housing, which then spins the wheel itself, so it's bolted here. It also holds the disc brake in place. And that's basically our system. So now Josh will talk a bit more about the suspension system.
So we as a suspension group are responsible for all the vehicle dynamics of the car, the actuation system, and the kinematic linkages. And the basis of the vehicle dynamics is the suspension subsystem on the car. As we know, suspension is responsible for isolating the body from the road inputs and react to the forces generated at the tire contact patch. And that's where the actuation system will come into the picture. So this year we have a very specific system on our car named Hero Suspension, where Hero stands for heave and roll. The important feature of this system is it is decoupled. Now what do I mean by decouple? On production cars, we have one spring and one damper on each vehicle, and anti-roll bar is used to stiffen it up. But for us, the heave motion and the roll motion are basically divided into different springs and dampers. This is all good, but it presents some challenges. This is a very neat and special design, but the challenge with it is setting it up and tuning it up so that it becomes a competitive solution for us. But the advantages of using this system outweighs the challenges. The key advantage of using this system is the ability to tune the car with a stiffer spring in the heave motion and the softer in the roll motion, along with independent damping coefficient, so that we can improve the tire grip during cornering and hence the handling of the car. The biggest update this year in the actuation system is the dampers. We are moving towards the shorter dampers. What this allows us is to make the system more compact, and hence we can reduce some weight in it, which is one of the goals for CFS22. Another specific part that we have focused more on is rotating bars, which transmits the load from the tire and pushrod to the springs and dampers. And this part requires additive manufacturing. Basically, they are going to be manufactured in 3D printable aluminum alloy. All the parts that are going to be 3D printed are topology optimized design. These also present some challenges during the designing. If you see this design, it's not very straightforward. It takes time, but we consider it as an engineering challenge to get it to work and simulating it so that we can have all our properties correct. And also, manufacturing of this kind of part requires specific methods. But the highlight for this part is it's going to be lightweight, and it's going to save a lot of manufacturing time for us. It's going to save a lot of manufacturing work for us. Another crucial system in suspension design is to achieve the all-important ride and handling balance. Vehicle dynamics is used in conjunction with the kinematics to study the behavior of the vehicle during different dynamic conditions. As Herman mentioned, we are moving to 16-inch tires from 18-inch. So to compensate for that change, considering the packaging constraint, considering the target set by us for different dynamic parameters, we have to change our mounting points on the chassis so that keeping the same ground clearance, keeping the same ride height. So basically we simulated how the linkages will travel during different dynamic conditions, and that way we came up with how we are going to mount these linkages on the chassis so that we get better handling of the car, which is important for every vehicle. Our focus from now on is to build the compliance model. The basic idea here is to study the deflection of the suspension parts per unit force applied. Currently we are only using the rigid components while doing the simulation, But as we move forward, we are going to consider the elastic components such as suspension bushings, so that our model can become more accurate. We get more realistic data to validate our design. At last, I would like to show you some of the simulation videos that we actually perform. So this is one of the different simulations that we perform to actually check the behavior of the car during different dynamic conditions. So as you can see, the both tires are moving in the same direction, so we call it as a parallel wheel travel, and here they are moving opposite, so we call it as opposite wheel travel. And this type of simulation is used to check the behavior of the car whenever there is a bump or there is a droop on the road. And like this, we perform different simulations to check the behavior of the car in different dynamic conditions. To talk more about braking and steering, I will hand over to Maya.
Thanks. Yes, so yeah, this year we're implementing a driverless system, and this has required two completely new mechanical systems, one for braking and one for steering. Acceleration is done by controlling the motors, so we don't need a new system for this, but braking and steering has two completely new systems. So for the braking, as we're competing in both manual and driverless competitions, we need the system to be able to do both. So the brake system has still its hydraulic system that it has used before, but we have added a pneumatic actuation system to be able to use the driverless part of it. And we have two independent systems, and this is to be able to have one system for regular braking and then another emergency brake system to be safe. So the two systems use the same logic, but they are independent of each other. So as you can see here, we start with store the air, because the pneumatic system means that we are using air to actuate it. So we store air here in a tank of about 300 bars. Then we have a pressure regulator that regulates down the pressure. Then the air goes through the tubes here, and then it goes off to a manual valve where we are able to turn on and off the system as we want. And then it goes down here, goes into pressure sensors, so we can monitor that we always have pressure in the system. So if we, for example, lose pressure in the regular brake system, we apply the emergency brake system directly to be safe. And then we come to the brain of the actuation part. So this is a control valve where we are controlling the pressure, and with pressure we are therefore controlling the force we're braking with, so that we can brake with different forces depending on where we are on the track. And then we go down to pneumatic pistons here. So if we look closer on the pneumatic pistons here, we can see that they are directly connected to the brake pedal here. So when the cylinder gets air, it pulls the pedal in the exact same way as if the driver were to push the pedal. So the system is basically acting as a driver. And then for manual braking, we have also added a brake pedal for regenerative braking that Herman told you about. So this pedal is situated here outside of the normal brake pedal, which is the aluminum part in the middle here. And with this is possible to measure the travel of the driver's foot, so we know when to apply the regenerative braking, and in that way we can use less energy by still going the same distance, which means we can downsize the battery and score more points in endurance competitions. And then for steering, it's the same as with the brake system. We need to do it both manually and driverless. So we have a normal steering wheel as other cars. And then for the driverless part, we have a service steering motor situated here. So the motor is directly connected to the steering rack here. So when the motor spins, the steering rack will move back and forth, which will steer the wheels that are situated here. We're using a position sensor, so we know the angle of the wheels, so that we always know when to steer and how much to steer, depending on where we are on the track. And then to hold it together, we are using these metal 3D printed brackets where we use the topology optimization that both Siyash and Herman has told you about. So with that, I would hand over to the powertrain and Vishal.
As discussed earlier, we have a lot of additional components due to the driverless integration. We have spent considerable effort in packaging the components inside the monocoque. The considerations were made with several factors, but few of them is bringing the total weight distribution as central and as low as possible. The battery box is the heaviest component in the car. This year, the accumulator enclosure has been made lighter by incorporating more lightweight aramid material in the design. The cooling of the powertrain unit is done by two systems, the air-cooled and the water-cooled system. The motors and the PE box are water-cooled, while the accumulator box is air-cooled. And some key designs to note here are the cooling plate for the PE box, which is 3D printed to make the intricate cooling channels, and the air intake manifold.
We have accommodations for travelers this year, that's braking and steering actuation, control and implementation. For high voltage, we have a robust DC-DC solution. It is divided into two stages. So it also has soft start on input and output. It comes with temperature and current sensors and also has double the power output from the previous year. We also have a new charger this year, so that charges twice as fast and has better controllability. We have 30 in-house PCBs running from rear to the front end, covering everything and making everything happen. For this year, we have nodes, brakes, DC-DC connectors, motherboard, indication lights for logic and autonomous system. I'll hand over to Jonas for notes.
So the node system, the communication system, it's a bit difficult to visualize, but you can think of it essentially as the nervous system of the car, which means that it needs to be very quick and it needs to be 100% reliable. Sending the wrong signal at the wrong time could essentially mean the difference between the car taking the turn optimally or spinning off the track. And this has to be done for over 100 different sensors, and those sensors have to be available to all devices on the car. So it's quite a difficult situation, and we have to solve that somehow. And the way we've done it this year is that we have 6 different nodes, so you can see here, and they're all communicating over a CAN network, which means that the node that wants the information can take the information and ignore the rest. And if this node wants to communicate with this node, for example, we can directly send the message to that node, and we avoid the train that could otherwise happen that would cause delays. And what's good this year is that we have already managed to set up telemetry for this, which means that while we're testing in the testing season, we can see what's going on inside the car, even if it's driverless, and analyze the data, try to optimize the parameters, and make data-driven decisions to make sure that the car improves as fast as possible so it's ready for competition season as best as it can be. And as I said before, this is all very fast. We can essentially read the accelerator pedal from the front node, send it down to the control node where we convert it to the optimal torque we want, send it back down to the rear left node and out to the motors, and we can do that in under 10 milliseconds, essentially. And the magic that happens here in the control node is something that Andreas will be talking more about.
And as Jonas mentioned, with the help of all of these 100 plus sensors we're using, we're able to make sure that the car is behaving in just the way we want. And then you might ask yourself, how do we want the car to behave? Well, we have 4 tires. It's only contact patched with the ground. We want to maximize the grip that these tires have. So by using different control systems that is running in the background while we are driving, we are able to optimize and get the fastest possible lap time. And an example of this is traction control. Most people have it in their ordinary car. We're using the same, might be a bit faster, might be a bit more advanced, but we're using it. We're also, what's new is we're using a yaw rate controller, which basically listens of the driver. It sees how much he wants to turn. It notices how much the driver wants to rotate the car. And what we do is, as we have mentioned before, we have 4 different we have 4 motors, 1 in each and every wheel, and these are not linked together, so we can choose how much torque and speed we want on each and every wheel. And by doing this, we can estimate how much the driver wants to rotate the car, and we're able to send, for example, more power to the outside wheel and less to the inside wheel, and then we can make a sharper turn, so we get a way sharper turning radius. And how do we do this? So, from all the sensors Jonas talked about, we get all the inputs from the CAN. And what we use with this, we send all of the sensor data and all the driver requests into an estimation block. And what we do here is, with the help of Kalman filter and more, we're able to estimate the speed of the car, but we're also able to estimate how much does the driver want the car to rotate. And we calculate all of that in there, and then send that, the estimated rotation, the estimated speed and more, into a control block where we then figure out, well, if he wants to rotate this much to the right, how much torque does each and every wheel need? And then eventually we send this out to the CAN again, to the network that Jonas showed, and then it behaves just like the driver wanted. And what's been focused this year has been on fast iterations. We don't have much time testing, it's very limited. We want to make sure that once we're out driving the car, we want to be able to go through different iterations of software very, very fast. So what we have done is made sure that every parameter in the system is remotely tunable. And we have over 30 plus parameters that we can change on the fly remotely while we're actually driving the car. So there's no need to stop anymore, recompile the code, write it, and start up the car again. Now we can just keep on driving, keep on changing until we get it correct. And we also wanted to make sure that all of these solutions are very robust and they actually work. So what we have done already back in October last year, we implemented all this as much as we could into the last year car and made sure that it actually works on the physical hardware. And this works great if you have a driver, but what happens in the case if you don't? And that is what Bernardo and Kilian is going to talk about. The driverless system.
Yeah, so as a first-year driverless team, we focused a lot on robustness. We wanted to make a first base code that works well, is robust, and then next years they can improve on. So we made sure we have comprehensive code and documentation. That is our main goal. For this, we also decided to go for ROS 2. This was because of the great improvements they made over ROS 1 in terms of performance. More interestingly, we decided to use ROS 2 inside Docker containers. How we do it is we have multiple ROS nodes, each of them with different algorithms, and each of them run inside the Docker container. This way, we can develop on our own computer, in our Docker container, and it will run exactly the same on our computer or in the driverless computer. We also have it integrated into our GitLab CI. So every time we make a new code, it automatically compiles everything, creates Docker containers, and deploys it. So we can use it in the car. This makes it possible to change Docker containers inside the car in seconds. We don't need to shut down the car, we don't need to shut down systems. We just shut down one Docker node and put a new one. We also decided to use C++ due to its performance and great usability with ROS 2. As for hardware, we mainly focus on LiDAR, but we also have a camera. So we have a LiDAR, a camera, and an IMU plus GPS. Because we mainly focus on LiDAR, we don't need a heavy GPU or heavy processing unit. So instead, we will only use one CPU, which is an Intel i9, and 32 gigabytes of RAM, and a Coral Edge GPU to help us do small classification neural networks. And this is our pipeline. So we start, again, our main sensor is the LiDAR. So we start first with the LiDAR point cloud, and we use perception algorithms to try to find objects. After that, we have objects that could be cones or could be something else. So we run it to cone verification. And this cone verification will try to verify if it's a cone or something else. From this, we obtain cones, and we do path planning, which decides where the car wants to go. After this, we have a control system that controls the car, the steering and the pedals, to achieve that path. We also have state estimation, which estimates the position of the car and the velocity. And we have SLAM. SLAM is to map the track, so if we go multiple laps around the track, we know already the track, so we can go faster. So for perception sensors, again, we focus mainly on LiDAR because it's a precise measurement of position, and it's very predictable. It doesn't change much with weather conditions or lighting conditions, unlike the camera. Also, it's very computational light. We don't need a GPU. We can use only a CPU. That's enough for us. We also have a camera. We use the camera mostly for validation. So we get what we think it's a cone, and then we validate with the camera and decide which color the cone is with the camera. And that's crucial for us because we need to know where to stop. And those stopping locations is signaled by different color codes. For perception, so we start with a big cloud of points, a massive cloud of points, which is very difficult to process. So we first do some filtering. We take out the cones the points that are very far away and the points that are very close. After that, we try to detect the ground, as denoted here in gray. So we detect the ground and eliminate these points, and then it becomes a much lighter cloud. After that, we try to find the clouds of points, as denoted in blue. So these clouds should represent an object. The problem is these clouds have some points that have been removed by the ground removal, such as the ones in yellow, because the ground removal is quite harsh in terms of removing points. So we then recover the points in the reconstruction step, as denoted in yellow here. After this, we have full objects represented by clouds of points. So we then do cone validation with the camera and the LiDAR. We are very proud to say that this entire process takes under 5 milliseconds. Also, we are able to detect cones up to 15 meters, which is really good for us. And we expect to increase this number to 20 by competition. Now for path planning, I'll pass it up to Killian.
Yes, exactly. So now we know the position of other cones, but we don't know yet where to go. So that is the next step, to plan a path. And for that, we exploit the geometry of a track. So we use Delaunay triangulation, and what it does is it splits up, like it connects all the points with triangles. And if we then take the middle points of those vertices and then fit paths through that, we have a lot of potential paths that could all go like that could be our path that we want. And one of those is for sure also the middle track of the race path. And we only care about the middle track because the path is fairly slim. We don't have much room to go to the left or to the right, so that is sufficient. And then to choose which one is actually the best path, we have a cost function. And that cost function includes things like the angular change of the path or the standard deviation of the track width to then find the best path, which is here visualized in violet. And then when we have the path, we have to tell the robot or the car what to do. And that is then controlled. For that, we now have pure pursuit, as you can see here. And pure pursuit is fairly simple. It has a look-ahead point at a certain distance away from the car. And it computes then the angle, like it computes the steering and the velocity depending on that point. We additionally have a model predictive control, which is a much more advanced control algorithm. And what model predictive control does, it has a model of the car and it looks into the future. It computes what will happen in the future, and depending on that decides which is the best optimal control choice for the current state. And all of that, as you can see, it's in respect to the car. So we can only plan as far ahead as we can perceive cones. If we cannot perceive cones anymore, we cannot plan ahead. And it's all in the local frame, exactly. So what we are doing for that, to avoid that, is to use SLAM, which is simultaneous localization and mapping. And what that does is, in the first lab, it doesn't change anything, because we don't know yet how the track is. But doing the first lab, we can actually map everything and save in a global map where the cones were, where they were detected. That means from the second lab on, we know how the track is. We can plan much further ahead than our perception pipeline can detect cones, which means we can go much faster and have many advantages, and is also much more robust. For that, we use FastSLAM 2.0, because in our opinion, it is a good choice as it's less likely to diverge. And doing 2 readings of the sensors, it's not known which cone is the cone in the next reading. Like, when I have a position of a cone, I don't know where the cone is in the next reading. So for that, we have to associate the data, which we do with the joint compatibility branch and bound algorithm that is also used. So how does it look in a simulation? Here's a video from the local frame from the view of the driver. So what you can see is always the cones that are perceived by the perception pipeline. And they are shaking because we are obviously adding noise to the simulation to make it more realistic. And then the green path is the planned path, and the car then follows that path. And we have run it for a while. It ran a lot of hours without crashing, so that is quite reliable. Exactly. So, boiling everything down. We are a team from many different studies. We have a lot of different fields. It's a great engineering challenge to make that possible. We have challenges in software and electronics, and mechanics, and we try to combine that all together to build a race car, a robot, one could say, to drive as fast as possible and make that all work together. And that wouldn't be possible without all our great sponsors. So a big thanks to all our sponsors for helping us. A big thanks for anybody in that team and helping, and friends and family. Here again, the car, and we would now open to questions. And also, if you're online, please feel free to ask questions in the chat, and we will bring them up here, or obviously from the audience.
Yeah, question.
Top speed.
Top speed. Well, I think numbers we say 130 kilometers an hour. So it doesn't go too quick. The focus is more on the acceleration.
Yep.
What is the estimated weight? If you can say.
Frame?
Unfortunately, we don't want to reveal the weight, as that is quite a sensitive number, especially as we reveal at what speed the car can drive upside down.
Yeah.
Who will drive the car?
Possibly me, but once we get to competition season, we should look for drivers. It has to be a Chalmers student, and there are a lot of good drivers at Chalmers. So usually when we're getting closer to the season, we start recruiting. So we haven't decided yet.
How much could you estimate a percentage of how much it's changed since last car? I guess it's subgroup dependent, of course, but do we change a lot?
Do you want the questions answered per subgroup? Because it would be very hard for us to give an overall estimate.
Tell something about you doing a lot of changes every year.
I think a lot of subgroups have changed a lot this year simply because we are adding driverless. It is more weight, it is more things that we need to fit into the car, and it is more signals and everything we need to account for. So I think this year is a bigger change than most years.
Do you redesign everything?
I think everyone in the team has to take the driverless into account. Some more than others. Some literally focus only on driverless. Some focus more on some like extra weight plays different on the car. So I think it depends very much on who you ask, how much they have been affected. But everyone has been affected in some way.
Have you done something with the driver UI? Have you made any changes, or what can the driver see on the steering wheel?
So we have moved. We used to have the UI in the steering wheel. We have now moved onto the dash. So it's a bit easier for the driver, it's a bit higher up to see. It's easy to see. We've also made improvements so we have less information on the dash. We only have the things that are very necessary for the driver. Things as how much battery. For example, we don't show the battery until we're getting very close to it. So we're letting the driver know how, in an endurance run, for example, we drive 22 kilometers. We're letting the driver know if we're hitting the target, if we have enough battery to get to the end. If not, he doesn't need to know it. He needs to just focus on the driver. So I think we made it more simple and less information for the driver. Yep.
Do you predict that there might be any issues with cooling of the LiDAR? I'm just wondering if it can be temperature sensitive.
We've been testing the LiDAR for quite a few hours. Fortunately, even standing still, we managed to run it for 4 hours without overheat.
Okay.
It also comes with heat sinks, which we will place in the car. So while driving, it should not be a problem. Thankfully, we're also not going to very hot competitions. But
Yeah, firstly, thank you guys for a very nice presentation. I have a question for chassis.
Yes.
And it's about, you claim that you have increased in torsional stiffness.
Yes.
And I was just curious about how do you go about this when designing? How do you justify that you have a stiffer monocoque than previous years? And how do you design such that you achieve this?
Yeah, thank you for the question. So the first part we started with was identifying where on the car is it the weakest. So that would be taking last year's design and running that through the simulations that would show us what load case, using the load cases we have in competition, showing us where are the stresses the highest in the car and where does the car deflect the most at the moment. And then from that we redesigned the geometry around the cockpit area, because that was where we identified that was the weakest spots of the monocoque. So I did redesigning the shapes on the sides to have a more curved shape. We got higher torsion stiffness with the later simulations. We've also done work with layup to utilize the flexibility of carbon fiber to have more carbon fiber where we have higher loads, so where it does more use than in the places where it's not as loaded.
All right. Are you planning to run any physical torsion test on the monocoque, or?
Yes, we are. The monocoque is being manufactured as we're speaking. So as soon as that is done, we're aiming to do torsion stiffness tests to validate the simulations.
Thank you.
We have a question from online. They are wondering when we will reveal the livery.
Well, this will most probably be in the design reveal. No, sorry, the car reveal event we will host in somewhere around May, hopefully. And we'll reveal the entire car with its livery. Yep.
I have one question. What is the cost for such a car? I mean, not the competition, just the car. What do you spend for the car?
It's very hard to say, since we have a lot of sponsors helping with materials and things. But it's a lot. That is how much I can say. It is all made in carbon fiber, 3D printed metals, every single battery cell. It's the most performance we can get out of, like, we don't buy cheap things. We try to make the best out of the best car we possibly can, and it's expensive.
I guess what, if it's 500,000 or if it's...
It's over that.
1 million plus at least, but yeah.
Oh, way more.
And you're not getting paid for working.
No, so
it depends on where you want to draw the line, I guess.
Yeah.
Yeah, again, not all of it is from Chalmers pockets. A lot of it is from the partnerships that we have with sponsors.
We have another question from online. Is the car using ground effects for its aero package?
Yes, very much so. I mean, both the front wing, side structures, and the rear diffuser is very close to the ground, which means that ground effect is used, yes.
Yep.
How much better will the second lap be after you've already mapped cones?
So the thing is, especially, it depends on the controller, obviously, but what do you say? I don't know.
It's hard to say, but
it's hard to say. A few seconds probably. So it will be faster, but it also makes it more robust. So for example, if you have a wrong reading in the second lap, you know that it doesn't make sense because you know how it's supposed to look. So like, I don't know. Yeah, I guess a few seconds. But yeah.
makes it a lot more robust. Even if you knock down a cone, you still know the track. So it helps a lot as well.
And also to know where to stop and where to go. Yeah.
Yeah, question?
Which will be fastest, with or without the driver?
So yeah, for this year it will most likely be with the driver, because we started that year with the driverless system. So we have a lot of things to just build from scratch, to build up, and as we said, we try to make it useful for next year, so that next year can continue with what we did and improve on that. So for that year it will most likely be the driver, but we aim in the next years for sure that the driverless will get faster, and we do our best to make that possible.
there's very, you mentioned regulations somewhat, but we are very limited by regulations. Could someone give an example where that has been very hard to design around for this year?
If you want. Yeah, so for the brake system, the driverless brake system, as I showed you, there are two things of everything, because there is this rule: if a single point failure is occurring, so if one component fails, then you have to still be able to use the emergency brake or the other part of the brake. And this rule was a bit weird formalized, so it's it took a while to first get a hang of what they actually wanted, and then to design after it. So I really tried to get away not to have to use two components of everything, because it's increasing the weight and the complexity of the system. But it's so that was quite it was quite hard.
We have another question from online. How is your car different from other cars at the competition? Are there any designs or innovations that you think could give you an edge over the other competitors?
Yeah, I think maybe our carbon fiber rims could be one thing. We're not the only team, but we are quite a few teams, I think, who are using carbon fiber rims. So our rims are lighter, and so we have less rotating mass, and we have also this flexibility that you told us about. So we can get a lot of parts inside of the wheel package with increased performance.
Yeah, just the fact that you can completely change the geometry based on what you need for your particular powertrain is very, very good.
Exactly, so it's both the bits and components, and then also this offset of where the middle is in the rim, so we can change it for dynamics and steering geometry and things like that. It's very beneficial.
And no questions online?
Where do you buy carbon fiber rims?
Sorry, can you repeat the question?
Where do you buy carbon fiber rims? Can you do that?
We do manufacture the carbon fiber rims ourselves. That is one of the 97% that is manufactured in-house by us.
And you design them as well, yes?
Yes. If you want to tell something about it.
Oh, about the design. Sorry, I didn't really hear. So they are designed. So first you have the tire, and the tire, the place where we buy the tire from gives us the surface that we want on the rims to be able to fit the tires perfectly on it. And then so this is the first thing to consider, and then also it's the interface with the gearbox and the uprights and wheel package, so we can fit everything. And then it's the offset of the rims, so that we can, for suspension, so the steering geometry. And then we have those things to take into consideration, and then we design it, and then we need to see how thick they should be, like how many carbon fiber layers, so that they will hold up. We want to use as little as possible. So like this year, it has been a challenge to get them try to stay in the same weight, because we have higher load cases, because we have more components on the car. So the car is going to be heavier. So we have had to add layers in some ways, but we have managed to find other places from last year's streams where we could remove layers, so to make the weight approximately the same, but with the same, or with higher load cases.
Another question from chat. Have you decided on a name for the car?
Who wants the honor?
You want to take that one?
Sure, I take it. Yes, we have decided on. We have decided on the name Hilbert for the car.
How so?
Who wants the honor?
There were a lot of discussions during when we decided that we should come up with a name for the car, but in the end we chose what we had available in front of us, which was the traditional pizza that a lot of people in the team eat, which is the Hilbert pizza, and therefore the car is named Hilbert.
We can say that the car is built on this Hilbert pizza, because we are.
Exactly, that's what powers the engineers that build the car.
No other questions? Okay.
Maybe I've got one question to Aero. Since this year you've got DRS for the front wing as well, is it somehow coupled? Because I mean, when both of them are opened, center of pressure will change its rotation. So I was wondering if you took that into account, or will you do that later when you will be designing how much the flaps should open?
Yes, we will. And also, so previously when only the rear wing has open flaps using DRS, the center pressure is changing, as you say. We're only doing this on the straights and we're closing it before we're braking when we need the downforce. So having the DRS on the front wing as well as on the rear wing actually makes the center pressure change less than it did previously, which is good. But yes, we will make sure to simulate the specific angles we want, and also discuss that with people in the suspension subgroup and the kinematics of the car.
You mentioned a lot of simulations, but do you do any testing? You mentioned the carbon fiber panels. Do we do any other testing?
From the chassis side, we do crash tests and material tests. So that would include different types of material tests. But for us, the point is just to determine how strong are the various parts of the monocoque. Other testing.
For aerodynamics, we're hoping to go to the Volvo wind tunnel when the car is somewhat finished, at least, later in spring. This has been done some years, some not, since it is quite difficult to get a spot at the wind tunnel, but we hope to get there this year.
And also for driverless actuation, we are planning on pretty much assembling the whole systems outside of the car before the rest of the car is finished, and do the physical testing on that one. So we know when we put the system into the car, we should be pretty sure that it's actually working.
And as you saw in the video, we had the tie rods for the suspension geometry are also made of carbon fiber tubes. And to test that these will be able to take the load cases, we also use tensile tests to test how much load can we flow through these without them or their mounting points breaking.
For software, we're also working very closely with electronics. So we basically have the whole low voltage system already built up and working. And we do that to make sure that there's no issues with hardware connecting or communicating with each other.
For driverless, we mount all the sensors and the computer in a small cart we can roll around and test everything while we don't have the car. That's the way we do it.
So you have a lot of 3D printed components. Which method of 3D printing are you using, and where will you outsource it?
That's a good question.
Well, we don't have our 3D printer responsible here, but you can speak with them after the presentation.
I think we should wrap it up then. And I want to thank you, everyone that has come here today. And we're open for mingle. Everyone is outside, so just come and ask questions about the car. And we will have someone that knows it. Those are questions. Yep. Thank you.
Ja.